Welcome to the second lecture of analysis of several variable, and the second topic for this course is introduction of Rn, and then we'll have linear subspace of Rn, basis dimension, and equally linear product in Rn, and then continuous functions. So before going to the Rn, we discuss about the cross product. So two sets A and B, the cross product is given as AB in a pair where A belongs to A and B belongs to B. So the elements of A and B. So as an examples, let's have here R2, which is given as R cross R. So here A belongs to the real number and B belongs to the real number. So this can be graphically present as like this. So let's R in the x-axis and R also in the y-axis. Then take A as x, value of x, and B as a value of y. Then the pair A and B is given as the member of R2. So since we can take any arbitrary A and arbitrary B, so therefore whole plane will represent as R2 cross R2. Now this idea can be extended to R3, R4 and so on Rn, where R3 can be written as R cross R and R4 is R cross R cross R cross R for R. Next we will try to get that how we can write the elements of Rn. So let's X is a member of Rn, then X can be written as x1, x2 and so on up to xn, that is n number of the entries. Or in some cases we also write it in the column vector as x1, x2 and xn in a single column. For example, R3 0 0 0 belongs to R3, 1 2 5 this is belongs to R3, 1 2 4 6 0 3, so this is, you'll see there 6 entries there, so this is belongs to R6. Now we can write 1 1 1 1, so this is belongs to R4. Next we need to know the algebra of Rn, the entries of Rn. So let X is x1 x2 to xn belongs to Rn, and y is equal y1 y2 and yn belongs to Rn. Then the addition x plus y can be given as x1 plus y1, means for addition of the first entries, then addition of the second entries, and continue addition of the nth entries. So each entry you have to add with similar position entries, then we can define the addition on Rn, and the addition also belongs to the set Rn. For example, let's 1 2 4 plus 3 2 1, which are members of R3, and if you add them, it will be 1 plus 3, 2 plus 2, and 4 plus 1, which is 4 4 5, and it is also member from R3. If x belongs to Rn and y is Rm, then x plus y is defined if n is equal m. For example, x belongs to R3, y belongs to R4, then x plus y cannot be defined. Next is that how to define the scalar multiplication on Rn. So let's x is equal x1, x2, xn. This is belongs to Rn, and alpha is field, which is from the field, which is here is real number. Then alpha x, the scalar multiplication, scalar alpha with vector x, can be given as alpha x1, alpha x2, and alpha xn. That is, the each component of the entries of x will multiply by alpha. If we write in the column form, then it can be written as alpha x1, second row alpha x2, and then nth row is alpha x. So if xy belongs to Rn, then x plus y belongs to Rn, and alpha x belongs to Rn. So therefore, the scalar multiplication and as well as the addition are close for Rn. So therefore, Rn is a vector space with usual addition and scalar multiplication. The previously the addition defined in the previous slide, and the scalar multiplication, that is known as the usual addition and usual scalar multiplication. Okay, so now the question is, if it is a vector space, then what are the zeros of Rn? The zeros of Rn is given as 0 Rn, which is equal 0 0 0. That means n entries of 0. Okay, and the inverse of this entries is given as, means if for any x belongs to Rn, the inverse will be the negative of that vector. So negative means here minus 1 we have to multiply, and by the scalar multiplication you will have minus x1, minus x2, and minus xn, which is also belongs to Rn. So therefore minus x is the inverse of the vector x belongs to Rn. So therefore each x belongs to Rn, there is minus x for that vector which is the inverse of that x. For example, x is equal to 5 minus 6 3 and R4. Then inverse of x is minus x, which is minus 2, minus 5, 6, and minus 3. Now if you see that if I add x plus minus x, then it will become 0, which is the 0 or identity element of R4. We finish the second section, introduction of Rn. Now we'll move to our third section, which is linear subspace of Rn. So first we'll give you definition. So a subset E of Rn is known as linear subspace of Rn if the 0 of Rn belongs to E and x plus alpha y, the linear combinations of two vectors x and y, which is also belongs to E. Okay, so let's have examples here that will show that which is subspace, which is not subspace. So we take W is a subset of Rn with the conditions that that first entry is x1 is equal 0. So W, capital W, contains all the entries from the Rn in which the first component is 0. So we have to show that this is a subspace of Rn. So since x1 is equal 0 and x2, x3, xn all can be any number which is belongs to R as which is belongs to the set W, which is Rn, and specifically if first one entry is 0, then it will belongs to W. Now if we take so clearly if x2, or you can say generally xi is equal 0 for all I is equal to 3 and up to n, then the entries x is equal 0 0 0, which is belongs to set W. That means 0 Rn is belongs to W. Now if you take y is equal 0, y1, y2, y1 is 0, y2, y3, and yn, which is belongs to W, then x plus alpha y for any scalar alpha, you will get the addition as 0 because 0 plus alpha 0, it will be 0, and then you will have x2 x3 xn and 0 alpha y2 alpha y3 and alpha yn. So if you add them, so you will get it 0 x2 plus alpha y2 x3 plus alpha y3 and so on. You will get xn plus alpha yn. So therefore the first entry is here 0, and we can say that this addition x plus alpha y is a member of W. So therefore W is a subspace of Rn. Okay, now come to our next example, and in this case the first entry is greater than equal 0, and we have to show that this is not a subspace, or we will verify that it is a subspace or not a subspace. Okay, now since x1 is equal 0, so clearly the first entries can be 0, and other entries since from any real number x2 x3 xn are any real number, so therefore that they can be 0. So therefore 0 0 0, which is the 0 of the vector space Rn, can be a member of W. Now to show the other properties, we can to show the other properties, we can take it by examples. We take 1 x2 x3 and xn belongs to W, because the first entry is greater than equal 0, so we fix it any number. You can fix it in by any number, and we fix it, the first one is 1, and second entries we are taking, the first one is fixed by 2, and the other entries are y2 y3 and yn, that belongs to W. Now we will try to do the scalar we will try to do the linear combinations of these two vector by taking, let's say, alpha equal -1. So therefore you got the first entries minus second entries, so x plus alpha y, which will be x, which is 1 x2 x3 xn minus 2 y2 y3 and yn. So then we will have here -1 x2 minus y2 and so on xn minus yn. So whatever x2 minus y2 x3 minus y3, we don't bother, but the first entries is -1, which is negative, so it does not belongs to W, as that condition of the W is that the first entry should be non-negative. So therefore W is not a subspace of Rn. Now another example is here, that the subset W is equal from Rn, and the condition is that the first entry is x1 is the x2 plus 1. So in this case we have to show that it is not a subspace. So first we will try to see that 0 is of Rn is belongs to this W or not. So for that we take, let x2 is equal 0, because each entry should be 0. Now if you take x2 equals 0, and also we can take that x3, x4 and xn all are 0. But if we take x2 is equal 0, from the relation x1 is equal x2 plus 1, you will get the first entry is 0. So therefore this Rn, 0 of Rn, which is all entries are 0, is not in the set of W. It cannot be. So W does not contain 0 of Rn. So we can conclude that this is not a subspace of Rn. So in general, the vector Rn, a vector from in the W can be given as x2 plus 1, x2 and xn. So same way we can take it y2 plus 1 and then y2 yn, this is also belongs to W. So this is the second way to verify that W is not a subspace. So now if you add them, just x plus y, then you will get it here x2 plus y2 plus 1, then x2 plus y2, and so on xn plus yn. Now look on this, in the first entries is x2 plus y2 plus 1, and second entry is x2 plus y2. If you subtract them, then it is difference is 2, not 1. So therefore it's not belongs to W. So W is not a subspace of Rn. So we finish the third section of our course of modulo and in module 1, and remaining will cover in the next lecture.